So thanks everyone for joining the session today. So I'm Tom from AWS here in Vancouver. So I'd firstly like to thank the conference organizers for picking such a great location that's 1 block away from my office. So that kind of helped. That was pretty handy getting across. And so at AWS, I work as an applied scientist, and I help internal and external customers deploy MXNet models. So the subject I'd like to talk about today is ONNX, which we've heard a few times mentioned in presentations, and then taking ONNX all the way to the edge and looking at edge deployments with ONNX. So quick agenda, what we're going to look at is just look a bit more detail into ONNX. We're going to look at how to create ONNX models or find them, look at a visualization tool, then look at deployment options, and lastly, just briefly talk about optimizations that we can do with these ONNX models. So what is ONNX? So ONNX, as we've heard, is a common format for neural network models. So every framework previously implemented their own model format, so you'd get quite a large degree of lock-in to a framework. And model researchers would have to pick a framework, tool developers would have to pick one, and you wouldn't get that cross-compatibility across frameworks. So having this standardized format is obviously beneficial, so it allows researchers to share their models. It means you can use a lot more of the tooling that's been provided around neural networks and exchange between the frameworks. And so ONNX is this interchange format that stands for Open Neural Network Exchange Format. And the key data structure here is the graph. So we're looking at a computational graph. And the nodes of this graph are certain operators that are going to be applied to some input data. In addition to having a set of operators that have been defined in ONNX, you have different types of metadata that you can attach to the operators and the graph as a whole. And then the operators are implemented in each of the frameworks. So that's both from an import and export perspective. You can depends on the framework. Some frameworks, you just have the import capability or export capability. MXNet is one of the frameworks where you can go both ways. You can train a model and export, or you could just import a model and run it for inference. And the different sets of software that interact with ONNX. So we've obviously got the frameworks that I mentioned. Then you've got the runtimes and compilers. So we've got NVIDIA with TensorRT, TVM as an example of a compiler. And then lastly, it's just some visualization tools. So we're going to be looking at Netron. So this is just to highlight that there's a large number of partners that are supporting ONNX. So as AWS, we're supporting ONNX. We've got Facebook, Microsoft, and a huge number of others, including ARM. So that's a good sign. So let's start at the beginning. Where do we get ONNX models from? So a few different sources. Most likely starting point for a lot of users will be to go to a model zoo. And there's actually a distinct ONNX model zoo that has a number of pre-trained models for a lot of different tasks. And that's been added to all the time. That's increasing quite a lot. There's obviously model zoos for lots of different frameworks as well. So maybe you found a certain computer vision model for a certain framework. You can then use ONNX to export that model and use the rest of your software to process that model. Then on the other side of things, if you've got more bespoke requirements, you can obviously train your own neural network in all these frameworks and then export to ONNX to use the whole process. And then there's a middle ground, which I think it will be quite common for a lot of users here, is what's called fine-tuning. So you take a model from a model zoo that's already been pre-trained on a huge data set, like ImageNet for computer vision, and then you have a smaller data set that you own that you can fine-tune the model to. And so that's an example that I'd like to run through today of fine-tuning a computer vision model. And to do that, the two tools that I'll be talking about, one is Apache MXNet, which is a framework that I've been working with, and we want to do this on AWS SageMaker. So let's just introduce those two a little bit later on before we look at any code. So one consideration is the model that we're choosing for Edge. When we're looking through this model zoo, there's going to be lots and lots of different options for us. So I'd just like to talk about a few of the trade-offs that we're going to have here. So we obviously are interested in the model performance. It could be accuracy for your use case. But there's trade-offs with the amount of computation that's required to get that accuracy and then the size of the model. So a once upon a time state-of-the-art model was VGG16. And a typical benchmark for this is its accuracy on ImageNet, which is an image classification task across 1,000 different classes. And so that achieved 71.5%. But that came at the cost of a huge amount of computation and in terms of the size. So there was 138 million parameters for that model. But more recently, there's been developments on much smaller models. So one example of that is the MobileNet. And you get roughly the same accuracy, but for much, much less on the computation and the size. So here, order of magnitude, less parameters. So it's going to be much, much more efficient. And then you'll see the likes of SqueezeNet models as well. There's just a few other variants. So that's what you should be looking more towards for edge devices. So what makes these models special? So it comes down to one of the convolutional layers. So this is just one component where the saving is made with something called a Depthwise separable convolution. So I'm not going to run into too much of the details behind this convolution, but in a regular convolution, you look across the spatial dimensions and all the input channels at the same time for a given output channel. So here the kernel is being applied across the 3 dimensions of an input. But with a depth-wise separable convolution, you split this process out into 2 steps. So the first step, you just look across the spatial axes, and you treat each channel separately. So in this example, we've got 3 input channels. That means after the first step, we've still got 3 input channels because we've done this spatial convolution across all the 3 channels independently. And then the second step is we look across all the channels, and we apply a 1-by-1 convolution. So we're not looking at the spatial dimensions anymore. And then we can change that to give us the number of output channels as we need. So we get the same input and gives us the same output. But in between, we've saved on the number of parameters that we need from both of those 2 kernels. So we've gone from 432 down to 75. And then if you looked at the number of computations that need to be done, we've cut that down significantly as well. So we're looking, in this case, 1/5 less parameters and computations. So for our MobileNet example, now that we've said that that's a good model for edge, just want to run through an example of fine-tuning that on the Caltech 101 dataset. So ImageNet is where it was pre-trained on from the ONNX Model Zoo. And then we can download the Caltech dataset, which has a different amount of classes, and we can see how that performs. So I'm just going to hop across and actually try and dive into some code very quickly. Shout if you can't see the code that I'm about to show, but I'm going to zoom in a little bit. Okay, so can everyone read that? Yep, okay. So this is an example of running MXNet on, actually, sorry, I'm just going to jump back because I was going to give a quick introduction on MXNet and SageMaker, which will then hopefully make this notebook make a little bit more sense. So let's just hop to that now. So yeah, just wanted to introduce MXNet a little bit more. So this is the framework of choice by Amazon. And one of the key things I'd like to talk about is the Gluon API. So it's a high-level API for MXNet, and it tackles the problem from an imperative approach. So you can define the network as you run through code. You don't have to create the symbol up front beforehand. So that gives you a lot of flexibility because you can create dynamic graphs. The other benefit is that it makes the code a lot more debuggable. So you can actually set breakpoints in your model, and as you're adding operators to your graph, you can actually inspect the values of the arrays, the values of the kernels, and see exactly why your model might not be working. This is great if you're developing your own model. And then with Gluon, you get the benefit of the symbolic graph optimizations as well, because you can go through this process called hybridization that takes you from this imperative approach to the symbolic approach. So a little overview as to what Gluon code will look like. These are just, I'm calling out the main sections here. So the first thing we need to do is obviously create our data. So this is an example with CFAR10, but in the notebook we'll see the Caltech dataset. We define something called a dataset, which is responsible for delivering single samples or single images. And then with neural network training, you often want to work with batches. So we have a data loader that's responsible for batching all those samples and doing the shuffling. And this is across multiple processes with lots of different workers. Then we have the model definition. So here we're using a model from Model Zoo of Gluon rather than ONNX. And then we want to define a loss because we want to optimize something. And the way this optimization is done is handled by a trainer that's going to manage the parameters and work out how to do the optimizations. And then the last thing you'll see with Gluon code is the training loop. So we loop through all our data, and for every batch that we get, we do a forward pass. So there we call our network with some input data. And then we call a backward pass, which is going to compute all the gradients. And then we do something called a trainer step, which is going to use those gradients and work out how best to change all the parameters of your network. So they're the key blocks that you'll see with Gluon code. Now, AWS SageMaker is a really handy service of AWS if you want to get started training neural networks quickly. So the first component to SageMaker is the notebooks, and that's generally what we class as the build stage. So you can spin up a notebook instance that has Jupyter installed, all the different frameworks, and will have CUDA installed, so you can use GPU training right out of the box. Then when you've built your model and you want to train it on a larger data set, there's really great functionality for training distributed. So they use the concept of containers. We've got Docker containers running on all these instances that are spun up for you. So you don't have to handle the server connections on how the weights are distributed and sent between the instances. There's an automatic model tuner that uses Bayesian optimization methods, so you can select hyperparameters for these training jobs. And then when you're happy with your trained model, there's a deploy method that will create an endpoint for you, so that makes the process from build to deployment much, much easier when you're working on the cloud. So now, if we look at the notebook, it should make a little bit more sense. OK, so we've got the imports. And the one thing I'd like to call out on the imports is ONNX itself is a submodule of MXNet. So it's in the contrib package. This part, we're just downloading the model from the Model Zoo. That is just a URL for this particular model. And we do the extract of that file. So now we have something that is of .ONNX format. So this is our ONNX file. We download our data set. Just in this case, Caltech 101. It's got 101 classes, I presume. So here's a variety of those classes. The first Gluon code we get to is creating the data sets. And there's a data set called image folder data set where you just point it to a folder. And that's going to work out what classes are. And then this is easy to run. So this would be an example of one of the images, which is a motorbike. Now, when it comes to fine-tuning the ONNX model, we can call import model with the path to the ONNX model, and that's going to give us a MXNet object. So we've got an MXNet symbol, and we've got the parameters of that model as well. When we think about fine-tuning, it's quite often that you want to take the first layers, but you don't want the last layer. So here we've got code that will slice off the last layer, which is usually a fully connected layer, and that's much more dependent on the data set you're working with. So because this was pre-trained on ImageNet, that part has got 1,000 classes. But for Caltech 101, we want to change that because we've got a smaller number of classes. So we slice off the last layer, and then we create, so that's a symbol block for the first part, and we create our own dense layer. So with Gluon, we've got a number of different neural network models and blocks, they're called. So here is a dense block, and we specify the number of classes in Caltech. We then initialize the parameters of this new layer, and we just combine it with the start of the pre-trained model. So we create something called a hybrid sequential block, where we take the pre-trained, and that then gets passed into our new dense layer. This is just the training loop, so we saw an example of that. And now, if we look at what the predictions would look like, this is if we just took our pre-trained model on ImageNet and gave it some images from Caltech. So it would get the predictions wrong, mostly because these images are not classes in the ImageNet data set that the model was pre-trained on. But now if we fine-tune on our new Caltech data set, the predictions from the model are much better and they're accurate because these images are of classes that we've fine-tuned on. And lastly, now that we've pre-trained our model, we can go ahead and save it. So the method for saving an MXNet model is we can export our MXNet model with the export method and define a path, and then use ONNX MXNet when we export the model. This is going to do the conversion from the MXNet model to ONNX, and then it's just going to give us that ONNX file. So we've gone through, we've imported the ONNX model, done the fine-tuning on our own data set, and now we've exported it. Okay, just a quick mention of how to visualize these files. So one of the tools that I often use is something called Netron. You can load in that ONNX file, and it will create a graphical representation or visual representation of that graph. And you can click on individual nodes and inspect some of the parameters, such as how many filters a convolution's got, what the inputs were. So it's just a really good way of inspecting. So now moving on to deployment. So we've heard the reasons for and against cloud deployment and edge deployment. If you're looking at cloud deployment, then I mentioned SageMaker has this deploy method once you've trained to get an endpoint. Also, another option is to use AWS Fargate. This is a service that manages deployments across containers. And in the containers, you could be running some kind of model server. So TensorFlow has got serving, and MXNet, there's a model server for that too. So that's some option that you could use. But then, obviously, we've heard about all the benefits of edge deployment. That's why we're here. So obviously, we're going to get lower latency. We save on bandwidth. Privacy could be a concern, so that's why we want to deploy on edge. And the ability to operate offline is key. So for that, AWS provides a service called GreenGrass, and we'll take a quick look at that. And then obviously you could be doing your own custom deployments here, building all the infrastructure yourself. So an overview of what GreenGrass is. The core component of GreenGrass that you'll see is something called a GreenGrass group. So this is a collection of devices, one of which is designated as the GreenGrass core. And the GreenGrass core manages a few different things, the way it connects to the cloud. So it's managing the authentication and authorization of all the devices. It's managing the shadowing. So if this group falls offline, it's going to do the buffering of all the messages and the updates. And it will manage over-the-air updates to all these devices too. So for a deployment of an ONNX model on GreenGrass, what components will we have to do? So the first thing is the device itself. And if you look at GreenGrass, they've got a number of pre-compiled frameworks for a certain number of devices. So if you're using Raspberry Pi, for example, you can download a pre-built version of Apache MXNet and run that on your Raspberry Pi. Then you'll connect that to the GreenGrass group. And the next step is to define the resources. So device resources are things like cameras or USBs that are on the devices, and machine learning resources. So this is where you'll take the ONNX model, package it up, compress it, and then send it across to all the devices through this model resource. Next thing, you may have heard of AWS Lambda, which is the ability to run functions on the cloud and not manage the servers yourself. Well, we take the Lambda function and put that on the edge through GreenGrass. So you can define a Lambda function in the same way, and that will then interact with the resources that you've defined. So it can access the device resources and has access to your ONNX model as well. And then if you look at the package from the pre-built MXNet, you'll see example Lambda functions of how to use that there. And then optionally, you can set up subscriptions to your GreenGrass group. So if you want to send the predictions back to the cloud, that can be handled automatically with subscriptions. And you don't always have to have that connection to the cloud. It's just going to batch things up and send them when it can. Okay, and the last thing I'd like to talk about, and I realize there is a talk afterwards in a lot more detail about this, but I want to give you an overview of how to optimize ONNX models. So the first thing is look towards half precision, if possible. So I think the Mali GPU has operations on float 16, so it depends on what framework you're using, whether you can use these. Then quantization, if you're looking at int 8, then you have to look towards calibration to make sure you're doing this properly. And there's some experimental examples and features in MXNet to be doing this. And then lastly, you should be looking towards compiling your model. And we've seen examples of that previously, but the example I'd like to run through is TVM, which we'll hear a lot more about in the next talk. And so the main overview of what the TVM stack provides is you have the compiler element, and then you have the runtime. And then the compiler takes in various front-end models, so you can use ONNX directly. That is one of the front ends for the TVM stack. Then it gets passed through something called NNVM, which is going to handle the graph optimizations. Then TVM, which will manage the tensor operations, and you specifically target certain devices. So here, when you're doing the TVM step, you can specify whether you want to use LLVM, which would be used for ARM devices, or CUDA if you're working with GPUs, NVIDIA GPUs. And the output of this compile stage will be a library that then you can run on the TVM runtime, which is much, much lighter. And will give good speed ups. So just a quick overview as the types of optimizations that TVM stack will offer. The NNVM part is the graph optimizations. So we can look at pruning and fusing. And TVM offers tiling and vectorization. And there's many more things that these do. These are just 2 examples of each. So pruning. This is simplifying the graph for inference. So while you're training, it's useful to regularize your model to prevent it overfitting and using things like dropout. But when you're looking at inference, you don't need to do the dropout. That's not something you want to apply. And you don't want to have to check whether you're in training mode or in execution mode. So it's best to just prune these nodes out. Fusing. So if you've got a graph that has a number of operations, one after another, oftentimes you don't need to store the intermediate values from the convolution to the ReLU. You can just apply the operation in a single step. So these operations can get fused together, which gives a much better speed up. And in the case of Depthwise convolution, which we saw before, it doubles the speed up. It doubles the speed of the Depthwise convolution if you use fusing with TVM. And then there's also techniques called folding, where if you've got convolution and batch norm together, those operations can be applied together in the same step too. Now if we look across to the tensor optimizations, which are much more specific to the device that you're going to be compiling for. One example is tiling, where you actually reshape your input in such a way to make better use of the cache. So more of the data that you're using, either from the input data and the kernel, could be used in the cache. And vectorization, where you don't want to apply the same operation to every element in your array. You can just take the 2 arrays and do a single operation together. So these are just a few quick examples. And then with TVM, there's a great feature called Auto TVM, which is going to actually work out the best levels or amounts of tiling and vectorization and parallelization to do for a given hardware. So it's essentially hyperparameter search if you come at it from a modeling perspective on the architecture. So yeah, just to wrap up, in summary, we looked at where you can find ONNX models from the ONNX Model Zoo, and then an example of fine-tuning with MXNet. We saw Netron is good for visualizing the model. GreenGrass is an option if you're wanting to manage a large number of edge devices in a group, and then TVM stack is something you can look at when you're optimizing the models. All right, thank you.
Thank you, Tom. Is it fair if I start with a question? Every framework has its own model zoo. TensorFlow has its own, MXNet has Gluon, Caffe has its model zoo. And you mentioned that ONNX has its own model zoo as well. Is it a different one? Is it a conversion of the other zoos? How does it work?
So the aim with the ONNX Model Zoo, at least, was to provide the code that was used to train the models in the model zoo. So a lot of the other frameworks, you have the pre-trained model, but you don't know where it's come from. So that's been one key thing with the ONNX Model Zoo. There hasn't been too much work in converting the models that have been pre-trained into the ONNX Model Zoo because of that reason. So you want to have the training script. But more work is being put in from a few different partners to build this Model Zoo out.
Thank you.
There is a deep lens device, edge device, that you've done in a cooperation with Intel. Could you please shortly explain how it works with the details you showed here? And are you able with that device to do the inference on the very device, or you're doing that in the cloud?
So for deep lens, yeah, the inference is done on the device itself. So you'll see through the AWS console, you'll be able to use pre-trained models and do the fine-tuning step again. But then it goes through a separate optimization step, specifically for, I think Intel have managed that optimization for that device, because I think it's running Intel Atom. And so that speeds up the models a huge amount, and then you can run on the actual device itself, not just on the cloud.
Okay. Thank you, Tom. That was great.
Thanks.
Thank you very much.